What if the earliest moment of the universe didn't disappear? What if part of it is still here? Not as light, not as matter, but as a signal we are only now beginning to detect. No stars, no atoms, no structure. Just extreme conditions and physics we are still trying to understand. And somehow, traces of that time may still exist. Think about that. Here's the problem. Everything we usually rely on, light, has a limit. It can only take us so far back. At a certain point, the universe becomes opaque. Light cannot travel freely. So beyond that boundary, we lose direct access. For a long time, that meant the beginning of the universe was out of reach. But maybe we've been looking in the wrong way. Let's ground this. Everything you see is made of particles. And most of what we know about the universe comes from light.
Light carries information. It helps us map stars, analyze galaxies, and measure expansion. But early on, the universe was extremely dense and hot. Photons kept interacting constantly with matter. They couldn't move in straight paths. So when we look far enough back, we reach a limit, a kind of cosmic fog. Beyond that, light stops working as a tool for observation. Pause for a moment. That means there is a region of the universe we cannot directly observe with light.
So the question becomes, are we permanently blocked there? Or is there another way in? Scientists began to rethink the problem. What if the early universe left signals that don't depend on light at all? Signals that could pass through extreme conditions without being scattered in the same way. Something more fundamental. This leads to an important idea in physics. Space is not just empty. It has structure. It can stretch. It can respond. And under certain conditions, it can carry disturbances. These disturbances are called gravitational waves. They are tiny changes in the geometry of spacetime. We have already detected them from events like merging black holes, but those are relatively recent in cosmic terms. So a deeper question arises. Could similar waves come from the very beginning of the universe?
Some physicists suggest the answer may be yes. They propose the existence of primordial gravitational waves, signals that may have formed in the earliest moments of the universe. Not from objects, but from the conditions of the universe itself. To understand this, we go back to a proposed phase called inflation, a period when the universe may have expanded extremely rapidly. During that expansion, tiny quantum fluctuations, always present at microscopic scales, could have been stretched enormously. From subatomic scales to cosmic scales. Here is the key point. Those fluctuations may have disturbed space-time itself. And that disturbance could generate gravitational waves. Not from collisions or massive objects, but from the dynamics of space-time during expansion. These waves would be extremely weak today, but they could carry information from a period that light cannot access. Let that sink in. question shifts. It is no longer just, what can we see? It becomes, what signals are still passing through everything around us, unnoticed?
And inflation may not be the only source. Some models suggest additional waves could form later as matter in the early universe evolves and clumps together. Another possibility involves cosmic strings. These are hypothetical defects in spacetime itself. If they exist, their motion, stretching, oscillating, reconnecting, could continuously generate gravitational waves. Not a single event, but a persistent background signal. What makes this crazy? This changes the approach completely. Instead of relying only on light, scientists can study spacetime itself as an information carrier. Gravitational waves interact very weakly with matter, so they are less affected by the dense early universe that blocked light. That means they could preserve earlier information more directly. Not perfectly, not easily, but potentially better than any electromagnetic signal. So the early universe may not be invisible. It may simply be communicating in a different form.
If primordial gravitational waves are detected and understood, they could help answer major questions. What happened during inflation? What physical laws operated at extreme energies? Did structures like cosmic strings exist? How did early fluctuations shape the universe we see today? These signals would not give a perfect picture, but they could act as a physical record, one that reaches further back than light ever can. However, this is still an active area of research. If these signals exist, they are extremely faint. Detecting them requires highly sensitive instruments and careful separation of signal from noise. Scientists are still refining models and improving detection methods. So this does not confirm any single theory, and it does not change everyday life. It does expand how we study the universe. It opens a possible window into a time when the universe was less than a second old, before atoms formed, before light could travel freely, before structure existed. And traces from that era may still exist today, right now. So, when we study the universe, light helps us understand its later history. Gravitational waves may help us reach further back. And that leads to a deeper question. If the beginning left traces behind, how much of it can we still uncover? Subscribe for more cosmic stories.